Welcome to Pharmaceutical Calculations, a conceptual approach, Lesson 35, Fundamental Concepts of Dosage Calculations, Part 3, Loading and Maintenance Doses. Our objectives for today are to define the therapeutic levels of drugs, describe the concepts of drug accumulation and fluctuation, and of course our ultimate goal is to use the therapeutic level of drugs along with other pharmacokinetic parameters like the volume of distribution and clearance to calculate optimum drug loading and maintenance dosages. Now, as we have discussed in our lesson 34 in our previous lecture, pharmacokinetics is all about plasma drug concentration. Plasma drug concentrations that elicit therapeutic effects are called therapeutic drug levels, and they lie between the mean effective concentration and the mean toxic concentration, as it is shown in this figure. Now, therapeutic drug levels are listed in all medical reference books where clinical pharmacists can retrieve and use it to adjust drug doses. Now, any plasma drug concentration that is above the mean toxic concentration will cause toxicity to a big percentage of the patients, okay? Whereas any plasma drug concentration that is below the mean effective concentration will fail to produce any therapeutic effect in a big percentage of the patients. What percentage of the patients? That is decided during clinical trials. And it depends on a lot of factors which we are not going to be discussing here. But definitely one of the big factors is the pharmacological indication of the drug. Now, the therapeutic levels is actually the range of these concentrations. From the effective concentration to the toxic concentration, okay? Now, obviously, the bigger the value of the therapeutic index or therapeutic window, our therapeutic index is defined over here for us, the safer is the drug as the mean therapeutic dose is much lower than the mean toxic dose, right? Now, drugs that have a very narrow therapeutic window require a minimum fluctuation of their concentration in the blood by carefully selecting the route of administration, the dose, and the dosing interval. So obviously this fluctuation is very important for us to control because we do not wish to exceed, to go above the mean toxic concentration or go below the mean effective concentration, all right? So let us now discuss the accumulation and fluctuation of drug in the plasma. Now, the drug accumulates only when the dose is administered before all the drug from the previous dose is eliminated. That's kind of common sense, right? But this paragraph here is very deep. So the drug concentration increases in the plasma for as long as the dose is administered with the drug entering the central circulation at a rate higher than the rate of drug elimination. So this is a very deep concept that goes back to the first order kinetics. The rate of drug elimination depends on the plasma concentration, right? And as you administer the drug at a constant dose and at a constant dosing interval. So why would accumulation stop? That's the question here. Accumulation will stop because as you administer the drug at a constant dose and dosing interval, at some point you're going to reach a concentration of the drug in the plasma such that the rate of drug elimination equals to the rate of drug input. Okay, so that's what we are referring here. Okay, and I know that many of us perhaps do not deeply appreciate what I have just described. We're just going to have to wait maybe a year after the course of calculations to really understand the essence of what I have just said. However, this is related to the next point, which you have to accept, as I just mentioned, until you take the course of pharmacokinetics where we're going to prove what I'm just writing here. So drug accumulation occurs for about 5 half-lives, after which time the drug concentration reaches equilibrium in the body, which is the so-called steady state concentration, okay? After about 5 half-lives, there is no more accumulation, And the drug elimination fluctuates within each dosing interval between peak and trough levels. That's because the rate of drug elimination equals the rate of drug input, okay, in the body. All right. Now let's discuss a little bit more about fluctuation. So fluctuation of the plasma drug concentration occurs when the drug is administered at dosing intervals, regardless of route of administration. So with constant rate IV infusion, so if you have an IV infusion, you're not going to have any fluctuation. No fluctuation, because it's a continuous infusion. There is no dosing intervals, okay? And this is the ideal way to administer drug that are very potent and they have a very narrow therapeutic window. Now, after each dose administration, within each dosing interval, the plasma concentration drops until the next dose. And that's why we have fluctuation, right? So the fluctuation is between a maximum or a peak concentration that usually occurs immediately or a little after each dose, and a minimum or trough plasma concentration that is observed just prior to the next dose. This magnitude is related to the elimination rate constant, and therefore it is controlled by the dosing interval. And again, this will be verified or it will be proved. The proof of it will be in the course of pharmacokinetics, but you will see and you will accept it in a minute when you see the plots actually. So for a constant dose, the larger the dosing interval, the larger the fluctuation of the drug plasma concentration. Okay? Let us take a look. So here we are. So this is a plot of an oral administration, at least the ones that fluctuate. Okay, so the green line is the IV infusion. It's a constant rate IV infusion. And you can see that there is zero fluctuation, right? So that's the green line. Now the red line and the dotted black line are oral administrations, because you can see that at 0 point there is zero concentration. So that is the concept of absorption here, right? Now the red dashed line is administered at 24 hours. So it's the same dose actually, total dose, right? So this is 24 hours, the dosing interval. Whereas the black line is 12 hours. So that should be, it's actually dotted. I see it as dotted, and maybe this continuous, okay. So continuous thick trace, all right. Now you can see that the fluctuation of the red dashed line is much bigger, much greater than the one than the black line, right? And this is exactly the statement that we have described. So this is, I'm just going to write it here. Tau is equal to 12 hours. And maybe I can change the color so we can see it here. Okay, just erase this. So this should be okay. All right. Now, therefore, this is so important for us. You need to make sure that when you carry out dosage calculations, the fluctuation does not exceed the mean toxic concentration, and it doesn't go below the mean effective concentration. Okay. Now, what's also important to say is that, as we have stated before, it takes about 5 half-lives to reach steady state. So if we consider here the half-life of the drug is 24 hours. So it would take about 120 hours. I'm just going to draw this line here, okay? So the drug accumulation is until this point. Before this point, the drug accumulates, and you can see the peak is increasing, right? But after 120 hours, you can see that it reaches a steady state, and then it just fluctuates between the peak and the trough. And the same goes for the black line, which is administered after every 12 hours, okay? It reaches a peak, and of course, it fluctuates between a peak and a trough. So fluctuation in pharmacokinetics is used only after steady state conditions, only 5 half-lives. I understand that the concentration fluctuates even at early time points here, but this fluctuation, it doesn't have a constant magnitude, right? It increases until the 5 half-lives where it reaches a constant value. All right, great. So the idea behind the concept of drug accumulation and fluctuation is, as I mentioned before, is to use the drug pharmacokinetic parameters to optimize the dose and dosing interval so that the plasma drug concentration is always within the therapeutic window. Okay. Now let us now move to the loading doses. And let me just change the color of my pen here. So you can go back to the red color. Okay. All right. The loading doses can be administered when maintenance doses are administered less frequently due to a relatively long half-life of the drug. And we have discussed this scenario a little bit in our last lecture. When a drug is administered for the first time, two major processes are taking place. So this is very important. Drug distribution and drug elimination, okay? Of course, drug distribution takes place much earlier and is much faster. And depending on the drug's VD, it can drain a lot of drug out of the blood circulation into tissues. That's why we are giving a loading dose. We are giving a loading dose such that we saturate the tissues, the organ tissues, much faster, so that we can reach therapeutic plasma drug concentrations earlier into therapy, okay? It takes about 5 half-lives of the drug distribution to reach equilibrium. After about 5 half-lives, drug distribution has reached equilibrium, and the only process draining the drug out of the central circulation is drug elimination. So this is basically the clearance, okay, which is expressed with the pharmacokinetic parameter, which is called drug clearance, and this is a constant parameter, dose independent, only specific to the drug. Okay, so different drugs have different clearance, and clearance is dose independent parameter. So this is important. So at this point, we administer the maintenance dose, which I'm writing as DM. Okay. Now, of course, when you give loading doses, you don't have to wait 5 half-lives anymore because you saturate the tissues earlier. That's the whole idea. It's a magical idea, and it does work. Now let's review some of the equations we're going to be using to calculate doses. Now the maintenance dose, of course, is calculated from the clearance. That's what we have here. And of course, we want to achieve drug plasma therapeutic levels. And in this case, because we are waiting for 5 half-lives, we have a steady state conditions, which are written as CSS. So plasma drug concentration steady state, okay? Now the denominator includes the salt factor in case your drug is given as a salt, and of course the bioavailability factor in case your drug is given by an extravascular route of administration. If you give it as IV, the FIV is 1, okay? Now the loading dose now is calculated from the VD, because as we described before, its purpose is to saturate faster the tissue organs with drug. So the DL, or the loading dose, is calculated using the plasma drug concentration, the therapeutic levels, which is CSS here, steady state conditions, times the VD over S times F. So let us actually now apply what we've learned and see how we can calculate loading and maintenance doses. So here we have a 66-year-old, 85 kilograms, 5'9" tall, 5'9", that's the height. Male, is to be initiated on digoxin for moderate congestive heart failure. His serum creatinine concentration was measured and found to be equal to 0.8 milligrams per DL, suggesting or implying no kidney impairment. So I have to tell you that some of these parameters, its physical interpretation will be taught later in other clinical courses. So at this point, again, we have to accept what the serum creatinine means if you're not familiar with. But this is what it means, okay? It means that the kidney are functioning properly. Okay. The population average VD and clearance for adults without kidney or liver insufficiency are 6.8 liters per kg. So this is my VD. And 262.5 liters per day. So this is my clearance. Okay. And the digoxin recommended therapeutic levels. So this is the drug therapeutic levels for digoxin is 0.9 nanograms per ml. Please answer the following given the information in the table below. So in the table, we have the bioavailability of the dosage forms available, commercially available, okay? So you can see the tablet bioavailability is 0.7 and it comes in 3 different strengths. The elixir, the bioavailability factor is 0.8, and of course the IVIM, the bioavailability is 1, that's why it's not written there, okay? So this is what we have to answer. Why would you administer a loading dose for digoxin? Calculate an oral elixir digoxin loading dose. Of course, the F for the elixir, I believe it was 0.8, right? So F is 0.8. Describe how you should administer the loading dose and compute, of course, at the end, the oral maintenance dose. Okay, so let's start for our explanation. So as we discussed, the loading doses are recommended for drugs that have a relatively long systemic half-life. So obviously our first task is to calculate the half-life. The idea is that it takes 5 half-lives for the drug to reach equilibrium in our body. So if the half-life is very long, it would take forever to stabilize the patient, right, and achieve therapeutic levels. So in order to calculate the half-life, we first have to calculate the K. And of course, K is calculated from VD and clearance. Okay, so we have the VD as liters per kg multiplied by the weight of the patient. We have a VD of 578. The clearance now is given in liters per day, and I'm just gonna convert that into liters per hour, because I would like to have the T-halves in hours. I could have left it per days too, that's fine, that's up to you. So clearance now is 10.94 liters per hour. Now K, the rate constant elimination, is clearance over VD, and that would be 10.94 over 578, so that's my K. And of course, for first order kinetics, ln2 over K is T-half, and I have a T-half of 36.6 hours. Now imagine, if you multiply by 5, that would take like more than a week, right? So that would be bigger than 1 week. You can't wait you cannot wait 1 week to stabilize your patient, right, to achieve therapeutic levels. That's why we have to give a loading dose. So this is what we have just mentioned there. So it takes 5 to 8 days to achieve steady state, and we need to give a loading dose to accelerate achieving therapeutic plasma drug levels in the body. So this is now my equation for the loading dose. CSS, that's the therapeutic levels, which was it was nanograms per ml, right? So here it is, 0.9 nanograms per ml. And here I converted it into milligrams, so divided by 1,000, divided by 1,000,000. It divided by 1,000 because I converted this into liters. So again, let me just write it here. So 0.9 nanograms per ml, that would be 0.9 micrograms per liter. Okay, so divide denominator and numerator. And that would be, if I'm gonna convert it into milligrams, divide by 1,000. So let me just write it here, over 1,000. That would be equal to 0.0009 milligrams per liter. Okay, so this is what I have there, times the VD, which is 578, over 1. This is the bioavailability factor for the elixir. And I end up with 0.665 milligrams. The digoxin strength of elixir is 0.05 milligrams per ml, is given in the table, right? So divide by the strength, and you need to administer 13 ml of elixir as a loading dose. Now, the administration of this loading dose will help achieve therapeutic levels essentially on the second day of treatment, immediately after the administration of the first maintenance dose. Now, how to administer the loading dose? Now, this is a very potent drug, and we need to monitor the patient. So usually, we will divide the loading dose in at least 3 portions. The first one should be half of the dose, and then if you see that the patient is not responding, give another 25% of the dose, and finally give another 25% of the total dose. So after administration of the first portion of the dose, if no signs of therapy or toxicity are observed within 6 to 8 hours, give the second portion of the dose, and so on and so forth. At the end of the loading dose, you administer the maintenance dose, okay? Now, we need to calculate the maintenance dose. Maintenance dose is calculated with the clearance, of course. So our therapeutic levels, again, the CSS is 0.0009 milligrams per liter times the clearance, which is 10.94. Now here, the maintenance dose is given as tablets, right? Because the patient now is stabilized, and the bioavailability factor of the tablet is 0.7. So carry out the algebra here is 0.01406 milligrams per hour, and you're gonna calculate the daily dose by multiplying by 24. And this is your daily dose, rounded up to 0.375 milligrams. You don't have a choice here. You have to round it up because you're gonna have to give tablets. The tablet strength was 0.125. So divide this total dose by the tablet strength, and you have 3 tablets a day. Okay, so as it's a good habit to avoid calculating doses with multiple strength tablets. That would be like very difficult for the patient. So the patient should take 3 0.125 milligrams digoxin tablets the same time every day, with or without food, and you have to be consistent there. And that's basically how we calculate the loading and maintenance doses. Now it's time for you to practice, and I have included one exercise here, 13.22, which is asking you, is testing your knowledge here. What would you change to make certain that the patient will experience at all times efficient therapy without toxicity? Obviously, this is bad, right? Because with the current dose and dosing interval, the patient may exhibit some toxicity, and at times he may not experience any beneficial effect, right? Because it goes below the mean effective concentration. So this is the mean effective concentration, and this is the mean toxic concentration. You need to adjust the dose such that the fluctuation does not exceed, does not get out of the therapeutic window. And here is an actual problem that you need to calculate the loading dose and the maintenance dose. And here is our answers. At this point, I would like to thank you for your attention. Until next time.